Hello, and welcome to another lesson for Math 1314 College Algebra. This is Section 1.2, Exponents and Scientific Notation. Our learning objectives for this section include using the product rule of exponents, the quotient rule of exponents, the power rule of exponents, the zero exponent rule of exponents, the negative rule of exponents. We will find the power of a product and a quotient. We will simplify exponential expressions, and we will use scientific notation. So let's get started using the product rule of exponents. Let's consider the product x cubed times x to the fourth. Both of these terms have the same base, but they're raised to different exponents. As you can see, this is raised to the third power and this is raised to the fourth. So how do we rewrite that as a single expression? Well, what we're able to do using the product rule is that we can add the exponents. So x3, x to the third power times x to the fourth power. Then we can go to x to the 3 plus 4. Anytime we have a product of exponents, we can then add those in the power. So 3 plus 4 is 7, which gives us x to the 7th power. Now, if you notice that the exponent is the product, it's the sum of the exponents in those terms. What that means is that when we multiply exponential expressions that have the same base is x in both cases, then we can add the exponents. This is the product rule of exponents. The product rule of exponents says that if we have a base a that's raised to the m power times base a raised to the n power, anytime we see that, that is a to the m plus n power. So at this point, let's consider an example. What happens if we have 3 squared times 3 cubed? These are just numbers, real numbers. We have the same base of 3, which means we can apply the product rule of exponents to say 3 to the 2 plus 3 power, or 3 to the 5th. Now we could simplify that, but the idea here is that we can add the exponents when we multiply products with exponents of the same base. Let's do another example. Let's do t to the 5th power times t to the 8th power. What does that give us? Well, again, going back to the rule that we started with at the top, we have the same base of t in both cases. So we're allowed to just add the exponents, which will give us t to the 5 plus 8, or finally, t to the 13 power. Let's do one more example. Let's do k to the 6th power times k to the 9 power. Ask yourself this question: do we have the same base? We have the same base of k. That means that we're allowed to use the product rule of exponents, and we can add the exponents. So that's k to the 6 plus 9 power, which is equal to k. 6 plus 9 is 15. And that's the simplest solution. We don't need to simplify any further. Let's crank it up just a notch. Let's go and consider using the quotient rule of exponents. Similarly to the way that we do the product rule, if we have an expression that is y to the m power divided by the same base, y to the n power, then we can simplify that to be y to the m minus n power, so long as it's the case that m is greater than n. So let's do an example. What if we have t to the 23 power divided by t to the 15 power? Well, we know that it meets the qualifications because 13 is greater than 25, and we know that we have the same base of t. As we've said before, the base has to be the same. So we can simplify this as t to the 23 minus 15 power. And what is 23 minus 15? 8. T to the 8 power. Okay, let's do another example using the quotient rule of exponents. Let's do negative 3 to the 6th power over negative 3. This is a little trickier than what we've done before. What is our exponent in the denominator? What is our exponent here? We have the same base of negative 3 in both cases, but what is this exponent? If we don't see an exponent written, it's understood to be 1. So 6 is greater than 1, so that meets our criteria. That means that this is equal to negative 3 raised to the 6 minus 1 power, or negative 3 to the 5 power. Okay, now we'll move on to using the power rule of exponents. What if we had an exponential expression that was raised to another power? Can we simplify that? Well, the simple answer is yes, we can use the power rule of exponents. Let's imagine for a second that we have x squared raised to the 3rd power. What does that really mean? Let's expand that out so we can really understand what we have. We have x squared, we have 3 factors of x squared. Which means in each case, we have x squared, excuse me, we'll go back, we have x times x times x times x times x times x. How many factors of x do we have in that case? Well, it's x times x times x times x times x times x, which is 6 factors of x, x to the 6th power. So we can write that as a more general rule to say that if we have a base, a common base a, raised to the m power, and that whole quantity is raised to some n power, then that's just equal to a to the m times n. You can multiply the exponents together. Let's do an example. Let's suppose we have x squared raised to the 7th power. Do we have a common base? Well, the base in each case is x squared, so that is the same, which means that we can multiply the exponents together to get x to the 14th power. Now let's do this definition so it's completely clear to us. This is the power rule of exponents. For any real number, let's call it a, and positive integers, m and n, the power rule of exponents states that a raised to the m power and that quantity raised to the n power is equal to a raised to the m times n power. And so that is the rule that will always be true, and that's our definition. Try and commit that definition to memory if you can. Let's move on and do another example. What if we have negative g raised to the 4th power and that quantity raised to the 4th power? Well, we know that we have a common base, g, negative g, excuse me, raised to the 4th power. So we have 4 factors of negative g, and then we have 4 factors of negative g to the negative 4th power, or to the 4th power, excuse me. So that allows us to say negative g to the 4 times 4 power, which is negative g to the 16 power. Let's move on to another rule. Using the 0 exponent rule of exponents. This is one of my absolute favorite rules that we can use. Remember back when we were discussing the quotient rule, we said that m had to be greater than n so that the difference between m and n would never be 0 or negative. What would happen if we said that m is equal to n? That would give us the 0 exponent rule. So let's say that m is equal to n, which is equal to 7. And we have t to the 7 power divided by t to the 7 power. Well, because those are the same thing, they cancel out and we're left with just 1. So what that means is that something raised to the 0 power is equal to 1. This is also true for any number that's non-zero or any variable representing a real number. So let's write out a definition. The 0 exponent rule of exponents. For any non-zero real number a, the 0 rule of exponents, excuse me, the 0 0 zero exponent rule of exponents states that a raised to the 0 power is equal to 1. Any real number raised to the 0 power is equal to 1. So let's do an example. What if we have w to the 8 power over w to the 8 power? Well, using the quotient rule, that's the same as w to the 8 minus 8, which is w to the 0 power. Using the 0 exponent rule of exponents, we know that's equal to 1. Let's try one more example. Let's say that we have t to the 3rd power, t to the 4th power, divided by t to the 2 power times t to the 5 power. Well, we can use the product exponent rule of exponents to say that we can add these. So that is t to the 3 plus 4 over t to the 2 plus 5, which is equal to t to the 7 over t to the 7, which looks very familiar to something we've done before. Using the the quotient rule of exponents, we can write that as t to the 7 minus 7, which is t to the 0 power, which is just 1. Okay, now let's switch once again. This time we're going to talk about using the negative rule of exponents. If we were to relax that condition that we discussed where m has to be greater than n, and we allow m to be less than n, so if m is less than n in our case, that means that m minus n is less than 0. Okay? So what if we had h to the 3 power over h to the 5 power? Well, the same rule applies, is that we can subtract the exponents. That's h to the 3 minus 5, which is h to the negative 2, but that's negative. What does that really mean? Let's rewrite it again. H to the 3 over h to the 5. That's really h times h times h divided by h times h, oh, not 5, h times h times h times h. So we have 3 factors in the numerator and 5 factors in the denominator, and I wrote 5 again. I have 5 on the brain. We have 3 factors of h and 5 factors of h in the denominator. So we can cancel those out until we're left with just 2 in the denominator, which is 1 over h times h, or 1 over h squared. So what have we found? We've done the exact same steps in simplifying, and we found that h to the negative 2 is the same as 1 over h squared. So what that means is that when we have a negative exponent, then we can use its reciprocal, 1 over that, and the exponent is positive in the denominator. So let's write out a definition for this. The negative rule of exponents. For any non-zero real number a, and a natural number n, the negative rule of exponents states that a raised to the negative n power is the same as 1 over a to the n power. You get the reciprocal. So let's try an example. What if we have negative 5t cubed raised to the 4th power divided by negative 5t cubed raised to the 8th power? Well, we can simplify that to negative 5t cubed to the 4 minus 8 power, which is negative 5t cubed to the negative 4 power. Well, let's go back for a second. The negative rule of exponents says that if we have a negative exponent with a real number base, then we can use its reciprocal. So 1 over negative 5t cubed raised to the 4th power. Let's do one more example. Let's do b squared times b to the negative 8 power. We know we can simplify this using the product rule of exponents. That's b to the 2 minus 8, which is equal to b to the negative 6. Using the negative rule of exponents, we can rewrite that as 1 over b to the 6th power. Let's move on now and consider how we find the power of a product. If we want to simplify the power of a product of two exponential expressions, we can use the power of a product rule of exponents to break up the power of a product of factors into the product of the powers of the factors. Let's consider pq to the 3rd power. We can begin by using the associative and commutative properties of multiplication to regroup the factors. So we know that that is PQ times PQ times PQ. Well, those are just products, so we can move things around. We have PQ times PQ times P times Q times P. Oh, that's all we get. We have 3 factors of each, so we can commute those around. P times P times P times Q times Q times Q, which gives us P cubed times Q cubed. So Let's write that out as a definition. This is the power of a product rule of exponents. For any real numbers a and b, and any integer n, the power of a product rule of exponents states that a times b raised to the n power is equal to a to the n power times b to the n power. So let's try an example. What if we have 2t raised to the 15 power? Well, we know that's equal to 2 to the 15 power times t to the 15 power Can we simplify anything further? Well, it becomes 2 to the 15 power, not in parentheses, times t to the 15 power. Can we simplify any further? Well, the 2 to the 15 power could be entered into your calculator. I don't know 2 to the 15th just offhand, but after calculating, it is 32,768 times t to the 15 power. Okay, let's try one more example. Let's imagine we have g squared h to the 3rd power, all raised to the 5th power. Well, let's go back for just a second to see that anything raised to the n power, that product can also be split off and raised to the n power. So this means that we have g squared raised to the 5th power times h cubed raised to the 5th power. Well, this creates another step for us because now we have something raised to a power that is then raised to a power. What rule does that get us to? Well, it's the power rule. It's the power rule of exponents, which tells us that this raised to this power is just the multiplication of those powers, which is g to the 5 times 2, which is 10, times h to the 3 times 5, which is 15. Okay, well, now that we've talked about the power of a product rule of exponents, let's find the power of a quotient. So imagine that we have the power of a quotient of two expressions. We can then use the power of a quotient rule, which says that the power of a quotient of factors is the quotient of the powers of the factors. Let's take an example. Imagine we have e to the negative 2 power, f to the 2 power, all raised to the 7 power. Well, this simplifies to be f to the 14 power over e to the 14 power. Let's rewrite it a little bit differently and look at the result of how this happens. E to the negative 2f squared raised to the 7 power. Well, that's just using the negative rule of exponents, f squared over e squared raised to the 7 power. And then we know, using the product rule of exponents, sorry, the power rule of exponents, excuse me, we have something to a power raised to another power. Then we're able to multiply those together, which gives us f to the 2 times 7 over e to the 2 times 7, or f to the 14 over e to the 14. Let's try another example. Let's imagine that we have p over q to the 3rd power, all raised to the 6th power. So how are we going to simplify this? Well, what we discussed before, the power of a quotient rule gives us the opportunity to give each of the factors that exponent. So we have p to the 6th over q cubed to the 6th. Well, certainly p to the 6th can't be simplified further, but q cubed then raised to the 6th can. And what rule does that use? Well, that uses the power rule of exponents again, and we can multiply those two powers together to give us 6 times 3, which is 18. So we have p to the 6 over q to the 18. Let's write the definition of the power rule, power of a quotient rule of exponents. There's a lot of work of exponents used in these rules. The power of a quotient rule of exponents. For any real number, a and b, and any integer n, the quotient, the power of a quotient rule states that a over b raised to the n power is equal to a to the n power over b to the n power. Let's do one more example. Let's imagine that we have negative 1 over w to the 3rd power, all raised to the 35th power. Well, the power of a quotient rule of exponents tells us that that power, 35 here, can then come inside those parentheses to give us negative 1 to the 35th power over w cubed to the 35th power. Well, we know that in the numerator, that's about as simple as we can get. But the denominator, we still have that issue of the product, the power of something raised to another power. So we can then multiply those exponents. 3 times 35. What is 3 times 35? Anyone? I believe that gives us 105 to the 105 power. Check that and make sure. Use your calculator. Okay. Now, we've used a lot of rules and we've learned a lot of rules. Now we need to move to use all of those rules to simplifying exponential expressions. Let's try an example. Simplify each expression and write the answer with positive exponents only. Let's start with x to the 8th power. I'll rewrite the 8 times x to the negative 12 times x. Well, how can we simplify this? Well, we can use the negative rule of exponents to move that x to the negative 12 to the denominator, which gives us x to the 8 times x over x to the 12. And then we can assume that we have a 1 as the exponent of just the x, which gives us x to the 8 plus 1 over x to the 12, or x to the 9 over x to the 12th power. And then we could go through and expand that and cancel it out, but we have the quotient rule, which says that we can just subtract those, which is x to the to the 9 minus 12, which is x to the negative 3, or 1 over x to the 3rd power, using the negative exponent rule once again. Okay, let's shift gears a little bit and consider a different concept. Let's move to consider using scientific notation. Let's start with a definition. A number is written in scientific notation if it is written in the form a times 10 to the n power, where the absolute value of a is greater than or equal to 1, but less than 10, and n is an integer. So again, a has to be strictly greater than or equal to 1, the absolute value of a, and strictly less than 10. So a is between 1 and 10. So let's consider converting from standard notation to scientific notation. Let's imagine for a second that we have the distance to the Andromeda galaxy from Earth. Actually, going to start a new page because this is a pretty big number. It is 24. I'll add 3 zeros and then 3 more zeros. And 3 more zeros. And 3 more zeros. Let's see if I have that right. 3, 6, 9, 12, 15, 18, 21. That's a lot of zeros. And we want to convert this to scientific notation. Well, our decimal is considered to be right here. And we need the base digit, going back for just a second, our A that we're considering has to be between 1 and 10. So the only way to do that is to get the decimal place right here. So we need to move the decimal this way, all of those spaces. So how many do we have to move? We have to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 spaces left. 22 decimal places left. So what does that mean? That means that this big number that we've considered, this 22 and a lot of decimal or a lot of zeros, this whole number that we're considering, if we move the decimal 22 places to the left, we get 2.4 times 10 to the 22 power, implying that the 22 spaces we moved were 10 to the 22 power. Let's try one more. What if we're going to convert from standard to scientific notation. Let's just imagine that we have just, let's see, 36 million, a number that we probably can work with a little bit more easily. How do we move that to scientific notation? Well, we have 1, 2, 3, 4, 5, 6, 7 decimal places we need to move. So that's equal to 3.6 times 10 to the 7 power. Okay? And in reverse, let's imagine that we're going to convert from scientific notation to standard notation. So example, 3.547 times 10 to the 14 power. We want to get that to standard notation, which means we need to move the decimal place to the right this time by 14 spaces. So 3.547. We need to move it 1, 2, 3. Okay. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And every place we had a space, we need to add a 0. So our resulting number is 3, 5, 4, 7, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 decimal places that we moved over. And that's our answer. At this point, you need to be able to convert between scientific to standard notation and back and use exponent rules. Now you can go and try some additional examples from your book, or you can go and do your homework on Edfinity. At this time, that will conclude our lesson for section 1.2. If you have questions, feel free to email me and I'll try to answer them as quickly as I can. Thank you.